This is 2.5 years of work. It's Sobe Sunset, and I believe this is the future of life on the water. This is the bulb, which has significantly improved our ability to get through the water at low power settings. As you notice, the bulb is an addition. It's anchored by the tube or sleeve, which is the basis for the spud pole anchoring system. The spud pole is an important part of the boat. Also visible are the pitch wing fins. Those are adjustable fins, similar to what a submarine has for change in elevation. And they will be functional, very useful in knocking down a head sea, avoiding pitch oscillations, which really are what induce seasickness. As you're looking up, you can see the spud pole, which is disguised under the umbrella. A very useful device in South Florida where the sun essentially is your enemy. Sobe Sunset is an interesting boat technically. You've seen that. You're probably asking, how does it work? Well, there's nothing new in the world, generally speaking. Everything has been done before. It was all invented 1 billion years ago in the Big Bang, physics. We've been working with my company Uni-Systems for Disney, working for Boeing, working for the Air Force, working for all the airlines, building automated equipment. I believe I can take those concepts and those systems that are already developed and apply them to recreational boating to create a boat like no other. To do this, we have a number of computer systems on board looking at each and every aspect of the operation and logging the data. To interface with this, we have what's called an HMI, a human-machine interface. Let me show you how this works. This is part of the HMI, the human-machine interface. This embodies what a lot of us refer to as AI, artificial intelligence. Now, I'm not a real fan of hiding behind artificial intelligence to make the world go round. Realistically, you could argue there is no such thing as artificial intelligence, but this is the closest thing to it. What we do, we collect over 40,000 parameters throughout this vessel. In this particular screen, we're looking at the HVAC, the air conditioning system throughout the boat. You can see numbers changing continuously. This is the pressure within the compressor. These are the temperatures of the chilled water circulating in the boat, which is all regulated by what we call AI. In other words, we've written a background program which speeds up and slows down the refrigeration compressor, turns pumps on and off to keep the most efficient use of our electricity to provide air conditioning, which in a subtropical climate like Miami and South Florida, that's really what boating is all about. If you look at statistically, most of the boats in Florida, 85% of the energy is consumed in air conditioning. Considering that there's 8,765 hours in a year, most of your energy is going to air conditioning the vessel. To build this boat and have it entirely dependent on solar energy, air conditioning was our greatest challenge. We started over with a complete new system, starting from the compressor on up, and built this system and the management system, which has cut our cooling load by 2/3. This particular vessel, about 100 feet long, about 2,200 square feet enclosed, required 15 tons of cooling when we started. Today, it's 89 degrees outside, the sun's shining, and we're doing it with 4 tons of cooling. An important part of every boat, of course, is the mechanics. So this is the engine room, although it's not really an engine room. It's air conditioned. The engines are in insulated soundproof boxes. And this is really a workshop, can be any area you want it to be. In each box is an engine, diesel engine. In front of each engine is an electric clutch. Next in line is what's called a PHT, a parallel hybrid transmission. Coming out the top is a shaft connected to an electric motor generator. Coming out the bottom is a conventional marine transmission, in this case a ZF transmission, which is driving the propeller shaft, which is driving the propellers. The electric motors are 480 volt AC motors. They are variable frequency driven by these port starboard variable frequency drives. These can turn the motors into generators, or they can deliver variable frequency electricity to drive the motors at any speed you want, either forward or reverse. The VFDs in their smaller models are all of these. This runs everything on the boat. All rotary equipment is driven by a variable frequency drive. The variable frequency drives are driven by DC power from the DC batteries. So we have a standardized 750 volt DC bus that feeds all this equipment. And this is the distribution panel for the DC systems. And this is the distribution panel for the AC systems, conventional hotel power. All the switchgear for all this equipment is inside this box. So the batteries feed these DC converters. These converters take the variable voltage from the batteries and turn it into a regulated 750. And this is all the equipment that makes that happen. In front is a process screen that tells us what everything is doing. This is various fuel valves that allow me to pull fuel from 7 different storage tanks that are mainly keel operated. This is a filtration system that spins it up to a high velocity for cleaning fuel. A problem on a boat like this, because we don't burn much fuel, preferably none. And that means the fuel gets old and it gets sediment, so we have to keep cleaning the fuel. A problem that some of the big boats don't have. They burn it up in a week. To start both the diesel engines, a conventional boat would have probably 4 big 8D batteries. In this case, we use a capacitor start system. There are no lead acid batteries. These are 3,000 farad capacitors. There's 12 of these capacitors in here. It weighs about 25 pounds. And it starts both engines so fast that it'd make your head spin. It weighs 1/100th of what the batteries would weigh, and it lasts forever. This is the way of the future for starting diesel engines. So the 2 engines on the boat are Scania. Scania is probably one of the most popular, efficient engines in the world. This is the engine. It's cooled with a heat exchanger, started with our battery system, and the real batteries in the boat, the real energy storage, is over here. Here's where the action is. This is probably one of the most unique and difficult parts of this build. By calculating how much energy we needed to make it through a 24-hour period, we determined that we needed this amount of battery. We have 2 battery banks. Each of them are 150 kW. This is the port battery bank, that's a starboard. They're identical, but they're separate. The batteries are each in independent compartments. Each one makes about 110 volts. They're series together to produce nominally 550 volts each, although that changes as the charge goes up and down. The batteries are managed by a complex battery management system, BMS, and they're water cooled. So each of these pipes brings cold water into the batteries to make sure we keep the temperature of the batteries plus or minus 5 degrees centigrade. The nominal temperature is 25 degrees centigrade. So they also have a vent in case of a discharge, in case anything goes wrong. And we have not completed that yet, but each of these vents will be piped with stainless steel tubing overboard. So if there ever is a discharge, it'll go overboard. Now, there really is no specification for marine lithium-ion batteries that's Coast Guard approved yet. We hope that what we've built here will be the basics for an approved battery system for boats like this. So this is about a 100-ton boat, about 100 feet long. This is the size space that you get. You can't put a ship's battery from a 1,000-foot long cargo ship in this kind of a boat. We need a boat battery system built for this kind of a boat. I think we figured out how to do it. These are the actual air conditioners that produce chilled water that's circulated through the boat for cooling, or for that matter heating. They're heat pumps, so they can do either one. So each of them are about 4 tons of cooling each. I'm just running one today because that's enough. In each one of them, there is this small coil that's called a de-superheater. So what we have done with these units, we take the hot gas off the top of the compressor and we run it through this heat exchanger, which circulates water with that small pump through this pipe, and it goes into the hot water heater. So all of our domestic hot water is created, is manufactured with waste heat from the air conditioning. Very efficient, saves money, saves equipment. This is a key part of the boat. This is an Evolution shaft drive system. What that means is there's a tube that goes to the back of the boat that's oil filled. We don't have conventional seals. We don't have cutlass bearings. We have a needle bearing at the back of this shaft that carries the weight of the propeller. But the important part of this is all the thrust from the propeller generating forward motion is offloaded onto the boat structure at this point. In a conventional boat, the propeller shaft is pushing on the transmission. Transmission is pushing on the engine, and the engine mounts have to be very stiff, which transfers vibration into the boat. In this boat, you don't hear the engines running. You can't perceive they're running. Now, important and very important for this reason, in an average boat where you have tight engine mounts, you have to synchronize the RPM of each motor or you get objectionable resonant frequencies. But because I'm building a boat that does not have rudders, I have to run both engines at different speeds because a boat never goes through the water straight. It's always going to want to go a little port or a little starboard, and you correct that by tilting the rudder maybe a half a degree. I can't do that on this boat. The only way I can make the boat go straight is to adjust the RPM, which would mean with conventional motor mounts, I would be listening to a resonant frequency forever. So it was fundamentally important that I used these style of thrust bearings, the Evolution drive, so that I was decoupled from a thrust perspective on the motors. It works great. So this is our charging system for all of our circulating heat exchanger water. We have a heat exchanger, obviously, for chilled water for air conditioning. There's about 40 gallons of water circulating around the boat. And to charge the system, this is our pre-mixed chemical. So we use a deionized water, we use an inhibited glycol with a bacterial agent, which means that our system will run for a long time without any chemical buildups, without any bacterial problems. This is the right way to do it. This system also charges up our electronics cooling, where we circulate water through this pipe system into all of our electric motors, all of our controllers, in order to get rid of waste heat. This electric motor is the stern thruster. So this is for a horizontal thrust, and it's a 480 volt, 3-phase electric motor. You can't help but notice that this is a very spacious engine room. And of course, that wasn't easy to accomplish. When I started, you couldn't walk through this space with generators and engines and exhaust systems and mufflers. You couldn't bend over. Now, we've not only got our 2 drive lines, but we've concentrated most of the machinery in the lazarette, and I've got this great workshop. Drill press, saw, we have welding equipment. We could make anything. We've got a hardware store. Everything you need when you're living out in the water. I've got a spray booth here, which gives me a chance to sand and grind. Every tool you can think of. Got storage for heavy duty stuff. I've got all my parts bins, all my bits and pieces that I need to get through the day. This is a great place to work. Another unique and very interesting feature of our power system is the way we ventilate the engine room. First of all, this space has no ventilators. It gets stale air from the cabin, and that's the only air that comes in here. It's been dehumidified and it's been filtered. The stale air from the engine room through power ventilators is pushed into the next machinery space. So again, the entire boat brings fresh air into the helm station at the top. It's dehumidified, it's filtered, and the boat is always pressurized with a regulated blower. All of that environmental air passes through all the machinery spaces so that we never have sea air inside of our electronics. Now, the engines consume a lot of air when they run. We have an intake blower that's regulated by a variable frequency drive that's tied to the throttle. So as we advance the throttle, the blower speeds up, which causes us to, so to speak, turbocharge or supercharge the engine with air. Now, when we do this, the engine is forced to consume its own heat. So we don't have any ventilation. We do not exhaust any hot air. And an engine makes a lot of heat, not only heat that's absorbed by the cooling, but also radiant heat coming off the engine block. In this case, the engine will eat the heat. We eat all of the hot air and it goes out the exhaust pipe. Now that changes the density of the charge air for the air cleaner, which is of some concern. Working with Scania, we've made adjustments. We believe this will be an effective way. In fact, it is an effective way. When we run the engines, they run great. We don't make any heat. Whatever heat we make goes out the exhaust pipe. So part of the concept of life on the water, living on the water for extended periods of time, is you got to be able to go to the hardware store, the grocery store. You got to go play tennis. You need a way to do that without making a big deal out of it. This is as easy as it gets. You step off the boat, you step into your little water taxi, you push a button, the deck lets you down into the water, you turn the key, and off you go to town. When you're coming back, you drive over the platform, you hit the button, the post guides you in, it comes up by itself, you get off the boat. This is part of the concept of living on the water. You've got to have a water taxi. This is it. This is a spud pull sleeve. The spud pull anchoring system is embedded within that. This is a very effective sunshade. It's built to withstand 105-mile-an-hour winds. It's not built to be taken apart, willy-nilly. It's all stainless steel. It's highly tensioned Tenera fabric, which is a very long-lasting, very strong material. We can walk on this. You can sunbathe on this. We've had 3-4 people up here. It's very strong. It's much stronger than it looks. It's built at exactly a 15-degree angle. That 15-degree angle is the pilot's line of sight from the helm station. So when you look down from the helm station, all you see is a pencil line because it's built at exactly what your eye angle would be. The seating area here is handy, and it's got a lot of nice little features like this. The table is built out of boat board, Simon boat board, which seems to hold up very well outside without any covers. It's non-staining. It's a pretty good material. We built a lot of our cabinetry out of the boat board. So the structure architecturally was challenging. We had to provide a lot of square footage for solar without disrupting the sleek look of the vessel. We chose aluminum pipe, and our connections were difficult, but they worked really well. So again, the roof is built for 105-mile-an-hour wind, and we think that's adequate, and of course it's a key to making it long-lasting and safe. We can see better in some of the details when we go up topside. The pipe structure that supports the roof, the solar panels, is a really important part of the boat, and it was critical to the architectural look of the boat. It worked out well. So this is the Tenera fabric that we mentioned earlier. It's Teflon Gore-Tex thread with Teflon extruded through it. It's a product called Tenera. It's made in Switzerland. Exceptionally strong, holds up good, has 40% light transmissions, so it feels good at night, feels good in the daytime. Filters out all ultraviolet light, and is a great platform for the solar cells. It also is cambered, and it's cambered so that rainwater will go into a gutter system that's hard to see, but it's built into the tube structure. And that's how we capture rainwater, which, as mentioned earlier, is an important part of trying to be energy efficient. Anchored to that tube structure up there is the lightning protection system, all of the navigation lights, the weather station, the satellite compass, the radar, and that's the exhaust system for the engine. So this boat is fitted with dry stacks, dry exhaust. We do not exhaust into the water. Right now, most boats exhaust into the water, and not many people are saying anything about it. But the day will come when somebody's going to say, why are you driving that oil-laden, polluted exhaust into our waterways? It's just around the corner. Dry stacks are more efficient, and I think it's the way to go. So this is a great outdoor area. It works with the Sky Lounge inside. It's a good cooking, entertaining, got a really high quality gas grill. It's built out of, again, boat board, which is an HDPE product. So it's impervious to the outdoor elements. And the two areas, the Sky Lounge plus this area, is really a high point of this vessel. So here's the ship's ladder from the main deck. It's equipped with an elevator. You never know when you need that. And this is the way to the flybridge. So this is the flybridge. It's an area that interacts nicely with the lower or the upper deck, which allows people to be at both areas and still talk to each other. For driving up here, there'll be a screen which is not yet installed, and the control system is portable, so you can drive the boat very effectively from up here. It's not outfitted yet, but we expect to apply some low-level furniture up here. And this is the structural system that holds up the solar panels. It's got 6 feet 4 inches of clearance. This is the last square inch of space where you could actually sunbathe. Otherwise, we've covered everything.